So once again, we have an interesting lecture for today, and that is probability distributions. Probability distributions. And once again, I'll try as much as possible to go slow based on your questions you'll answer so that you can appreciate the content. So the purpose is basically to understand and explain the following probability distributions: binomial, Poisson, normal, exponential, uniform, and gamma. Now, some of them will not go into details. Some of them, 3 of them will go into details, and 3 of them will not go into details at all. We will look more at the mean and then the standard deviation. The mean and the standard deviation. And then the probability of anything happening. The chances of anything happening given the distribution of that thing. Now, when we normally say distribution, what does it mean? Who can tell me? What do we mean by distribution? The distribution of something, like normal distribution. What do we mean by distribution? What does that mean? Who has a fair idea of what distribution means? In fact, if you are the sort of person who is even into business, and then they are bringing your goods, you have an idea about what I mean. So what do we mean by distribution? Who will be the first person to talk to them? Distribution. What does that mean? What is the meaning? What is the essence of a distribution? Yes, Henrietta.
Good morning. Sorry, I'm under the weather. Distribution means sharing something among people, like among a group of numbers of people.
Good. I like the word you said, sharing. Is that the word you said?
Please.
Yeah, sharing. So sharing here will mean that everybody will get a portion. Everybody will get a portion. And so distribution looks at that portion, how the whole of the thing looks like. So when you take the ages of everybody in this class, some will be 20, some will be 30, some will be 40, some will be 50. And by plotting these ages, you will be able to have a look at the entire age, the entire age. Now, the entire age can be measured numerically. And that entire is a mean. So on average, what is the mean age? Okay. Now, that will tell you the center of the ages. And then the distribution will look at how are these ages, gathered around that mean age. How are the ages gathered around the mean age? And that is what we mean by the distribution. In order to understand distribution, you got to know what a random variable is. Suppose you throw a die. We learned last week, okay, that when you throw a die, then we can have the sample space. The sample space is what we used to call the omega. So this is the omega, the sample space. And the sample space, because it's a die, the sample space will show 1 to 6 possibilities of showing. Okay. So you will have that 1 to 6 possibilities, pairs of possibilities of showing at any point in time. So what do we then mean by a random variable? And it's very important you understand a random variable now. Please, by the time I finish and you don't understand a random variable, ask. So a random variable is a particular number, in this particular case of a dice throw, okay, is a score on the first dice plus the score on the second dice. So what we mean is that if I throw a dice, the probability that that value that will show is a 2 is a random variable. The word random means that any of them have got a chance of showing. The word variable or variate means that that particular one is the one that stood out. So a random variable is that kind of variable that stands out in any particular experiment. But let's take it a little bit further. If you have that sample space, which is the omega, then the random variable depends on the sample space. Because first of all, there must be the sample space. And based on the sample space, you now get the random variable from it. So if the sample space is omega, then the random variable is x, which is a function of the sample space. And each of the sample space must be real numbers. And the real number is represented by this capital R. So what is a random variable? It is a variable whose value depends on chance. And it's true. In the case of a dice throw, if 1 is the one that will show, the possibility of that one showing is probability, it's a chance. So the random variable is one whose value is based on chance. It depends on chance. It's not any other variable. Your age is not a random variable. But if your age has got a chance of being selected from a lot of ages, in this case, your age now becomes a random variable because it is coming out of a random situation. So the probability of a particular random variable, which is written as something like this, P of x equal to x, should be understood as representing formal probabilities. Anytime you want to say that the probability of a particular random variable happening, this is how you write it. That's what I mean by a random variable. There are two types of random variables: discrete and continuous. Who can tell me quickly one of the things that characterize discrete and one of the things that characterize continuous random variables? Who can tell me? And by the way, I've shown you a graph of each one. What characterizes discrete variable? There's one thing that is very unique about discrete variables or discrete random variables or discrete numbers. You can tell us. One particular thing that characterizes discrete random variable. Very well.
Doug, please, they are whole numbers.
Exactly. They are whole numbers. Now, what other things are whole numbers that you know? Apart from the word whole numbers, you could have also used what numbers? Apart from whole numbers, what other word can you use? Charles?
Counting numbers.
Counting. Okay, counting. There is another word too. Somewhat.
Integers.
Integers. Very good. So you got to know those particular numbers. Now, the reason why random variable is a whole number or integers, positive integers, is why you can see that in the graph, you have them as standing on their own. Standing on their own shows that they are whole numbers. But then if you look at the continuous random numbers, they are decimal. They can be decimals. So it is a whole series of numbers. That is why you see that it is showing that distribution. So the distribution of a discrete random variable, it is what you see here, standing on its own, unlike the other one. Now, these are the definitions of a discrete random variable and a continuous random variable. A discrete one is where you have x, and it's a set of all the x's up to the total of the x, which is the xn. But then if you look at a continuous, okay, you can't easily count them because there are several things. So it becomes the union of all the intervals. So x now becomes the union of intervals within that real positive terms or that real numbers. So they involve measurements, whereas discrete involve counting. And that is why, so if I mention something like centimeters, would you say it's a discrete or is a continuous? Centimeters. Is it discrete or continuous? Be careful. Della.
Continuous.
Continuous. Age. Is it discrete or continuous? Age. Is it discrete? The way your hands went up with the first one, I was expecting that your hands would go up very quickly with the second one. Yes, Afia?
Discrete.
Age is discrete.
Age is not discrete. Okay. Age is not. You see, the way Africans count age, they count age as if it's like that. But age is a continuous variable. Who can explain why age is a continuous variable? I know you said that is discrete because of how you have been brought up, your programming. Your environment is what made you say that. Yes, Michael.
Yeah, age is continuous because after you attain a certain age, there are days, months, weeks, and months that can be added to that age.
Yeah, it's not even after. The moment you are born. Okay, I have a friend nearby. Okay, he told me that his son was just born. This was last year. And he told me 9 days later, he says that his son had been born and now he's a father. And I said, congratulations. He says, and I said, when? Okay, and then he said, oh, he's just 9 days old. He's just 9 days old. But you say that he's not even 1 year. That's how you say it. He's not even 1 year. Okay. But here, 3.5, 7.2, 8.9 are all part of the ages. So take note of how, ages are. Now, what about gender? Gender. Is it continuous or discrete? Gender. Salasi.
It is discrete.
It's discrete, yeah.
So it used to be discrete, but now it's continuous.
No, it's not continuous, please. It's not continuous. I know where you're trying to arrive at. I'll not even say that whether or not you are in Africa, it doesn't matter. It's still not continuous because whether you are bisexual, homosexual, or that, those ones are still going to be whole numbers, more or less. So, you're off, no? Yes, Johnson. John.
Yeah, sir, good morning. So my question is with regards to the age being continuous. So if you have to represent them in figures, right? And then let's say we have 3 years, 5 months, or 3 years, 6 weeks. And if I represent that as 3.6, and I represent the 3 years, 5 months as 3.5, how are we able to assimilate the difference that 3.6 is 3 years, 6 months, or 3 months, 6 days?
No, of course, if you want to now distinguish between that, you have to add more decimals. So it might be 3.64. Okay. First, you have to know that if you have 3 years, now, in terms of months, there are 12 months. So if there are 12 months and the person is 4 months, Okay? It will be 4 out of 12. And then you add that in decimals to the 3. But then you come to the weeks. Okay? And how many weeks are there? There are 7 weeks. So you now, and if the person is 4 out of 12 months, but in the third week or something, then you also now divide that if it is 3 days. Okay, so you now become 3/7. What I'm saying is that it's not strictly point something, it's point something something. It can go as many decimals as possible, and you can convert. Please, does that make sense?
Yes, please.
Yeah, you can convert. Okay, I mean, if you tell me that there are 366 days in a year, and I say that, okay, now I've clocked 50 days, you can find that in the decimal, can't you? It's 50 divided by 360.
Yes, please.
And you can still do that division and call it what? You call it in years. So you take your calculator, okay, and then you divide 50 divided by 366, which is 0.1366, blah, 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 years. Does that make sense, okay?
So then it means we have to normalize the data first, because if you are working in months, weeks, and days, it can be a bit confusing, especially if it's November.
Of course, it depends on what you are doing.
Months.
I'm just telling you the possibilities.
Okay.
I'm not saying that you should go and use that by force, isn't it?
Yeah, sure.
I'm not saying you should go and use it. I'm only telling you that it is possible for it to be in months, in weeks, in years. I'm telling you, go and check the record. The Guinness Book of Record, 2 women were fighting that their child was the 7th billionth child. One was in Hawaii, one was in California. My son is the 7th billionth child. They wanted to claim the ownership of the Guinness Book of Record. So now we have to go and check which child, because they were all born at the hour, 4:50, let's say 4:56 a.m. And so now they had to go and split the difference, and they had to use milliseconds, not seconds, milliseconds, to indicate that one child is 19 milliseconds older than the other. Okay, do you get a picture now? If one child
Yes, please.
is 19 milliseconds older than the other, you are talking about seconds and weeks and months. Even milliseconds is counted as age. Anyway, let's move on. You get it. I know you get it.
Yeah.
Tell more.
Doc, please, can age be treated as a mixed random variable?
What is a mixed random variable?
Having maybe a discrete and at the same time
No, it cannot.
Okay,
if you want
you.
to now in your mind treat it like that, fine, but it cannot. By statistical jargon, it cannot. It is what it is.
Thank you.
Yeah. Okay. Now let's start with the discrete random variables. Okay. And somebody can lower your hands now. So let's take an example. I've given a couple of examples. A typical example is when you roll a die twice. Okay. When you roll a die, the reason why the rolling of a die is discrete is because whatever you do, you're going to get 1, 2, 3. There's not going to be 1.6, 1.72. Okay. It's all going to be that. That's why it's a discrete particular random variable. Okay. Now, if you roll a die twice, okay, and then X is the number of times 4 comes up, the possibilities are S can be 0, 1, or 2. Who can explain why this is so? We've done this before. Okay? The possibilities are that X can be 0, because when you roll it and then the number of times 4 appears, when you roll the first one, 4 might not appear at all. When you roll it again, or many times, it's possible that 4 will appear only once. And it's also possible that, 4 will appear only twice. So that is why, in this particular case, the possibilities are 0, 1, 2. Let's take a throw of a coin. If you throw a coin 5 times, what are the possibilities? If X is the random number of heads, what are the possibilities? Let me see whether I can get that. Salasi.
So the possibilities will be 0, 1, 2, 3, 4, and then 5.
Perfect. Why?
Because there are there are possibilities you may not get a head at all, and there are possibilities you can get head once or twice or thrice, 4 times or 5 times as well.
Yeah, but you've not explained it. So each time you throw the thing, each time you throw it, you remember you're throwing it 5 times. So you threw it the first time, okay? The chances of you getting a head can be the first time. You will not get a head. You will not get a head. And so because you will not get a head, that becomes 0. The second time you throw it, you might get a head. The third time you throw it, you might get a head. That is another one possibility. Okay. Now let's go to the last one. You might throw, you remember you're throwing it 5 times. So the first time you get a head, that's 1. The second time you get a head, that's 2. Third time you get a head, that's 3. Fourth time you get a head, that's 4. Fifth time you get a head. So there are 5 times of getting a head in the 5 throws. And that means that if the last one you didn't get a head, it means that you got head 4 times in the previous throws. And that is why the possibilities are 0 to 5. So these are all examples of discrete, because the numbers you are talking about are whole numbers. Let's look at continuous. As for continuous, you've said it. They can give me examples of continuous variables. Who can give me an example? Give me one example of a continuous variable. There are several things. It happens in multiple. Janice.
It's age.
Age. What else? Samuel.
Temperature.
What else? Frederick.
Height.
Height. Right. He has said your own. Linda.
Time.
Wait.
Wait. Why are you all talking about human beings? Human beings matter. Michael.
Time.
Distance.
Distance. Very good. Time. All of that. Okay. So those are examples of what you might call continuous variable. Now let's look at the distribution. We've already said that the distribution, the probability distribution of a random variable tells you the possibilities and how those possibilities are distributed over the values of that random variable. And it is written as what you see here. Now, there are several distributions, and I want to just give you the formula for some of them, the ones we will not treat. For example, a particular random variable can have a uniform distribution on an interval of between A and B. And that is true if the probability density function is given by this. Now, the probability density function is the range at which the possibilities are happening. How the probabilities are happening. So in a uniform distribution, f of x, okay, has got a sort of a binary situation, but it's not actually binary, because the first situation is a 0. The other situation is 1 over b minus a when a and b are the outward possibilities. Either those ones happen, or so it's like when somebody tells you that you have the choice of traveling or the choice of not traveling. Not traveling is 0. But if you are traveling, you have to make the decision of whether you are taking the road by car, you're using the train, you're using the bicycle, the motor, the ferry. Okay? So now there are multiple possibilities in the second situation. That's a uniform distribution. And so we say that x is uniformly distributed, by writing X with a tilde sign, and then you can now put it into A and B. Another distribution is exponential distribution. Now check exponential distribution. Okay? It also has those possibilities, just like the uniform. Just like the uniform, but you have to now, once you've decided that the thing is happening, then there are possibilities of that happening. So the f of x is 0 or 1 minus the natural log, the exponent, raised to the power negative lambda, where x is either negative or positive or 0 inclusive. Now, this is a function, but the density function is what you see here. Okay. I'll later tell you the difference between the cumulative density function and then the density function. We will not treat this exponential. Okay. And this is how you write exponential distribution. Exponential distribution is given by x distributed as the exponent of the lambda, where the lambda here is the mean or the parameter or the rate at which the random variable is happening. The expected value of that random variable or the mean of that random variable is 1 over the lambda. And the variance of that random variable is 1 over the lambda squared. Again, we will not treat this very well. Gamma distribution is another distribution. Okay? Gamma distribution is a whole lot of exponential distribution put together. And that is why you can see that in this one, the top part here carries some ideas of the exponential distribution. And then you look at the right, you have x is greater or equal to 0. So you have a positive one here, but the 0 is a negative value because, of course, it's not going to happen at all. And so you need a rate and the shape of a density to be able to calculate gamma distribution. A lot of people use this thing in hospitals and sometimes in the air. Pilots use this gamma distribution a lot. And then, of course, the gamma function is given by the integration between 0 and positive infinity. And this is written as that. We call it the analytic continuation of the factorial function. And you can see that this symbol here is a factorial. And as long as you know the shape and you subtract the shape from 1 and take the factorial of that, because the shape, which is a R, must be a positive whole number. And if it is a positive whole number, then the gamma distribution, whenever the shape is 1, becomes an exponential distribution. And why? Because when the shape is 1, which is when R is 1, here, you will see that R being 1 minus 1 is 0. And 0 factorial is 1. You should check some of these things. You see that there. So a gamma distribution, when R is equal to 1, is an exponential distribution. Now let's get to the real ones that we are going to consider for today. And we are going to consider two discrete variables. And then we'll consider 2 continuous variables. So let's start with the discrete variables. And this is key. So I'm going to take some time here so that if you have some questions, you ask. 1, we already know this. We know that the conditions for a discrete probability function is that the probability of any particular random variable must be positive or 0. We know this. As long as it's even anything is positive or 0. But please remember that the greater than or equal to 0 means that it can be 0. In other words, the thing is not happening. Or the thing is happening. I just wanted to know that I don't want you to apply morality to it. Sometimes when you say that something is 0, our mind goes straight into negative. I can say that a man is 0, a woman is 1. when you're looking at sex. I can say that a man is 0, a woman is 1, or a male is 0, a female is 1. So that you don't have the idea that a male is better than a female, because that's not true. You know, and I can also say that good is 0 and bad is 1. So that you don't have attach morality that, oh, why didn't I make good rather 1? No, there is no, it's just a representation. And I hope you get that. The sum of the probabilities of the random variable is always equal to 1. We know this already. We know this long ago. So these are the two main conditions of a discrete probability distribution. Now, watch this. Let's take a practical situation. This is discrete, just a practical situation of a discrete situation. If you say that X is the number of TVs sold to the first 4 customers who enter a store, where X can take values, 5 values, which is 0, 1, 2, 3, and 4. Okay. If you have X taking those values, so just a second. Okay, if you have X taking those values, what it means is that the possibilities of remember, these are 4 customers. So who can tell me why is it that the first situation is 0? There are 4 customers. Okay. Why is it that the first value is 0? Dovi.
So there could be that possibility that the first customer who came didn't buy a TV.
That's it. And why is it that you have 4?
It could also be that all 4 came to buy TVs.
That's it. So those are the possibilities. You see, the reason why the 0 is important is that most of the time, people don't consider that. That doesn't come into the mind because our mind goes into counting numbers, isn't it? The first customer bought TV, the second bought TV, the third bought TV, the fourth bought TV. So now we have 4. But the possibility is that nobody bought TV. The next possibility is that only 3 bought TV. The next possibility is that 2 bought TV, 4 bought TV, 1 bought TV. Okay? And these are the random variables that you have. Now, on the basis of this, I can now conjecture the probabilities. I can guess the cumulative probability, or I can even look at the probabilities and have the probability of a customer or these 4 customers buying nothing, okay, not buying TV at all, is 0.4. The probability of them buying 1 TV is what? 0.25. The probability of them buying 2 TVs is 4, is 0.2. Okay. And then the probability that they are getting 4 TVs is 0.1. So you can easily compute these probabilities. Now, based on these calculated probabilities, you can now find the expected value for this random variable. How do you find the expected value? Well, the expected value or the mean of a discrete variable is just taking the probabilities and multiplying each probability by each random variable. So you take each probability, you multiply it by each random variable. You take the next probability, multiply by the next random variable. You take the next probability, multiply by the next random variable. You sum them, and that gives you the expected value. Let's look at it. Okay. In this same situation. Okay. So this is our original situation. These are the random variables, 0 up to 4. These are the probabilities. So you just take the 0 multiply it by 0.4, you take the 4, multiply it by the 0.1. You do that for each one, and then you sum them, and that will give you the expected value. So you can see that the expected number of TVs that are sold in a day is 1.2. So for any discrete variable, you can find the mean and, of course, the variance. This is a typical example. So the formula for finding the mean of a random variable, keep it in mind. How about this? Once you can find the mean, you can also find the standard deviation. And what is the formula for that? The formula for finding the variance is this. I'll come to that variance. But note that when you take the square root of the variance, that will give you the standard deviation. But first, let's look at the variance. Once you have the random variable x and you already have the mean, it's easy peasy to find the variance. Because you will now take each random variable minus the mean, each random variable minus the mean, each random variable minus the mean. Then you square. Okay? And then after squaring them, you multiply that squared number by the probability of that random variable, which you already knew from here. Normally, I would have let you calculate this yourself. Then you can appreciate it better. But please do that. Okay, do that. When I say do that, I mean you take each random variable 0 minus the 1.2, 1 minus the 1.2, 2 minus the 1.2, and then you square. Okay. And once you are done with it, the next thing you do is that you multiply each square by these probabilities. And then you sum them. That's what you have here. You sum them. And that will give you the standard deviation. So this is what you have here. The 0 minus the 1.2 will give you negative 1.2. The 1 minus the 1.2 will give you negative 0.2. The 4 minus the 1.2 will give you 2.8. You square each one of them. So the first one you get 1.44. The last one you get 7.84. You multiply that by the probability 1.44 times 0.4. That will give you 0.576. You do the same thing for each one. You sum these probabilities. And now you have the variance of the TV sold in the day to be 1.66. So based on this variance, you can take the square root of that, and the standard deviation of the daily sales is 1.29. So what we can say is on average, the number of TVs sold to the first 4 customers is 1.29 from the mean of 1.2. You will get something like this in the exams. Okay. But this is having identified, please note, having identified that this is a discrete random variable. Oh, by the way, who can tell me what makes this a discrete random variable? It's everywhere. What makes this a discrete random variable? This very thing. It's a clear discrete random variable. It's not continuous random variable. What makes this a discrete random variable? Frederick.
So the value of a TV being bought will be an integer or whole number. That is 1, 2. It cannot be half a TV or 0.3 a TV.
Oh, so it's not the value, but the what? It's not the value of the TV, but what?
The what?
Number. Say number.
The number of TV bought.
Exactly. So the number of TVs you are buying is not a decimal. You can't buy a quarter TV. You can't buy a 1/8 TV. You can't buy half a TV. You got to buy a whole TV. That's what makes this a discrete random variable. Yes, right.
Hello, Prof. Thank you. I want to find out how you computed the P of X. I mean, the 0.4, the 0.25.
This one.
You came out, yes, exactly. How like you came out with those values.
Okay. So when you have those probabilities could be given to you. And when they are given to you, you can now compute them yourself. So you could be given the probability. So in this very case, I've given you the probabilities, okay? The chances of them happening. That is what I've deliberately given to you here, so that you can now find them. But if you have not been given the probabilities, because you won't be given every probability, okay? You will not be told to calculate the probabilities yourself. So that is why I've given you the probabilities. Now, where you have to calculate the probability, I have to give you further information before you can calculate the probability. Because remember, I've not given you the distribution for you to be able to calculate the probabilities yourself. I've not given you the distribution. And so you don't know the distribution of calculating the probabilities. If you knew, okay, then you can now calculate the probabilities, but then you don't. So once I give you the probabilities, then you can now find those probabilities yourself. So please know that for this one, you have been given the probabilities, and you will be given the probabilities to calculate. But in some cases, you will be told to calculate the probabilities only if I've given you the distribution of this. I've not given you the distribution. I've only told you that it's a random variable. And there are several random variables. It could be binomially distributed. It could be Poisson distributed. You know, it could be other distribution, exponentially distributed. It could be any distribution. And because I've not given you the distribution, you cannot calculate the probabilities. But if I give you the distribution, you can calculate the probabilities. Opele, do you get it?
Yes, please. Thank you very much.
All right. Now let's go to giving you the distribution. Let's go to giving you the distributions. Then you can now calculate the probabilities. And the first distribution is the binomial. You all know this, that binomial, the word bi here means what? The bi.
Two.
The bi.
Two.
If it is not two, what is it? If it's not binomial, what is it? If it is one, what is it? God is not binomial.
Nominal.
I like that. That's true. It's called mono. Or better still, uninomial. And if it's more than two, what is it? Samuel.
The poly.
It's not poly. See, some of you are actually bringing so many things. Multinomial.
Multi.
I know where you're coming from. I know. Regression. You know, the first one, he says mono. And now, once you move from mono, you're going to poly. Anyway, let's move on. That was just a clip. So, before you can understand binomial distribution, you got to understand Bernoulli trie. There's a slight difference between the two. A Bernoulli trie is also a random experiment. Okay? There are only two possible outcomes, success and failure. And once again, I don't want you to see success as good and failure as bad. Keep that in mind. Okay? The probability of getting a success could be male. The probability of getting a failure could be female. The probability of getting a success could be female. The probability of getting a failure could be male. So keep that in mind. Never treat this with moral mind. Okay, let's look at examples of this Bernoulli tries. You can toss a coin. The chances of you getting a head or tail is a clear indication that it's binomial. Anytime you have a question on binomial, you got to distinguish whether it's a binomial, a Poisson, a normal distribution, or whatever distribution. These three are what I'm going to teach you the most. So you got to distinguish, but there are some keywords. One of the characteristics of a binomial or a Bernoulli trial is that there are two possible outcomes. Who can give me another example apart from this? Apart from exams passing or failing. Apart from, and nobody should give me male or female. And nobody should give me any other thing that I know already. Don't worry, you don't know what I know already. as long as I've not given you before. Day and night. Good. For you, you're thinking. Alvin. What else, David?
Yes or no?
Yes or no? What else? Don't go the easy ones. Positive and negative. Very good. Coco. Can you? Can be.
True or false?
Raise your hand and then say some. Charles.
Accept or deny.
Accept or deny. Very good. Okay. Salasi.
Defective or non-defective.
Defective or non-defective. Abrefi.
Close or open?
Close or open. William.
True or false?
True or false. Very good. I want some strange ones, not the easy ones, strange ones. Charles.
Win or lose.
Win or lose. Living. Livingston, what do you have? John.
Death or alive.
Very good. So these are examples, okay, examples of binomial situations. For example, when you do a medical test, what are the Bernoulli outcomes? Medical test. You can tell me the Bernoulli outcomes. Salas.
Positive or negative.
Exactly. Okay. Very good. Now, Coco said, leave her dead. Rainy or sunny. Hey, people are saying things, so people are thinking things rainy or sunny. Okay. Opposite of rainy is sunny. Eh? Okay. Yeah, making a shot or missing a shot is good. Inside or outside? Inside or outside? People are thinking. If you don't take it, you go and think what you don't think. Okay. As they say, you should say some. Okay. A customer buys or doesn't buy. Very good. Guilty or innocent. I love that one. That one is not common. Okay. A job offer, deny or accept. A pregnancy test can be positive or negative. So all of these are examples of Bernoulli trials. Okay. See, it's easy to say it now, but when this thing is subjected to a different situation, there are 4 properties of binomial. The first one is that there must be a sequence of n identical trials, where n is the number of observations or the sample size. They must be identical, meaning that they must be the same or similar. 2, the outcomes must be 2. 2 outcomes, success or failure. And we are not talking about morality here. 3, the probability of the success denoted by P should not change from trial to trial. So if you tell me that the chances of them winning the game, if you tell me that the chances of them winning the game is 80%, okay, and then they play again, and then they play again, and then they play again, that chance must remain the same. And the trials must be independent. The first one shouldn't depend. So the first one should not influence the second one. Or because they went to play at home, and then this one played away, okay, then the away, when it's a kind of a comeback game, so you can see that the previous one is influencing the current. We don't want that. These are the 4 properties, 4 characteristics, 4 things that must happen before a Bernoulli situation can happen. William, lower your hands. Now, let's look at our interest here. Okay. Our interest is to model the number of successes happening in n number of trials, and then finding the probability that a given number is occurring. That's it. That's the Bernoulli binomial distribution here. So we are going to let X be the number of successes happening in this, sample of 0, 1 trials. X is a number of successes occurring. It doesn't mean anything. It simply means that X is what you are interested in. That's what you are interested in. You could be interested in whether a person is getting HIV or not getting HIV. It's not about good or bad here. Okay, so that's the first one. This is the probability function for a binomial distribution. This is the probability function. Please write it down. Write it down in your book because you're going to use it for something. Write it down. It is when you write it that you can appreciate it. So I said before that what is the difference then between the Bernoulli and the binomial? Now, Bernoulli is a single trial, okay, and the outcomes are 2. Binomial is where you have multiple trials, and the outcome is still 2. That's the main difference. So the Bernoulli, okay, as you can hear the word, Bernoulli, okay, Bernoulli is a single one. Binomial is a multiple one. And we are always thinking about multiple, so that is why I'm giving it a binomial probability. Okay, so what is n? Who can tell me what n is in this? What is n? What is an n? What is this exclamation mark? William. William.
The n stands for the number of trials.
Okay. Afia, what is exclamation mark?
I was going to answer the end, but okay, let me see whether I can.
Try. 5 seconds. You see the way hands have been raised? All right. Coco, tell us.
Yeah, the exclamation is factorial.
It's a factorial. Coco, what is 0 factorial?
0 factorial is 1.
What is 1 factorial?
1 factorial is 1.
What is 2 factorial?
2 factorial is 1 multiplied by 2.
Are you eating? The way your voice is sounding. Are you eating?
No.
Okay, all right, okay. All right, so guys, for those of you who are not aware of this, that is a factorial. Okay? A factorial is when you take anything and then you now multiply it all through. Okay, so okay, let me start with 1 first. 1 factorial, okay, is given by 1 times 1. 2 factorial is given by 2 times 1 because the next number after 2 is 1. 3 factorial is 3 times 2 times 1. Okay, you are going descending. 4 factorial is 4 times 3 times 2 times 1. That's what I mean. This is for you, the babies. Okay, in case you don't know factorial, that's what you want to write down as part of your notes. X is the number of successes. N is the number of trials. P is the probability of success. 1 minus P is the probability of failure. All of them are here. Okay. So that is it. So when we say that find the probability of 6 successes in a particular number of trials, that is how you write it. And N, of course, is the sample size, and then the rest will follow. Okay, now, what is the mean and then the variance of the binomial distribution? Well, the mean of the binomial distribution, also called expected value, is always the sample size, the number of trials multiplied by the probability. It's simple. That's the mean. Keep that in mind. The variance is that number, is the mean multiplied by 1 minus the probability. So you better, it's like taking the sample size multiplying the sample size by the probability of success and multiplying it by the probability of failure. That is the variance. If you want the standard deviation, it's just a matter of taking the square root of this variance. Take note. Let's take a practical example. I want somebody to read this practical example for us. Who will do the reading? Who will do the reading?
Okay, sir, I'll read.
Yeah, who is reading?
Okay, sir, who is reading? Okay.
Okay.
Bob is concerned about a low retention rate for employees. In recent years, management has seen a turnover of 10% of the hourly employees annually. Thus, for any hourly employee chosen at random, management estimates a probability of 0.1 that the person will not be with the company next year. Choosing 3 hourly employees at random, what is the probability that one of them will leave the company this year?
Thank you. Yes,
Find that.
I like the way you read. Are you a news reader? Okay.
No, please.
Okay, so the first thing you got to do anytime you are solving probability distribution questions like this is not to calculate. The first is to ask yourself, is this binomial, Poisson, normal, uniform, exponential, or gamma? Now, since we are talking about binomial, then obviously you have concluded that it's binomial. My undergraduate lectures, I actually walk them through. I've mixed them so that I can dictate. But what is here that tells you that what we are doing is a binomial? Shows that what we are doing is binomial. Frederick.
The person might either be in the company or not be in the company. So it's success or failure in this situation.
Say that again.
The employee might be in the company or not be in the company anymore. So it's a success or failure situation.
Good. Good. Who has another idea? So what was the key word here? What was the key word that gave you the clue? What are some of the keywords that gave you the clue that this is a binomial question? Emmanuel.
One keyword is leave the company.
Leave the company.
Yeah, leave the company, yes.
Good. Keyword. So that is key. A leave or not to leave. See, guys, believe me, when I bring Poisson into the picture and I mix the two, if you don't take care, you'll not even know which one is a binomial, whether you should use binomial formula or Poisson. Anyway, so once you have gotten it, now you write a binomial formula and identify the element. So let's start with the identification. In the formula, we need to find our n. What is the n in this question? We need to find our n. What is the n in this question?
It's 3.
It's 3. Very good. What is the p in this question? Because we need to find our p. What is the p in this question?
0.1.
Good. And what is the 1 minus the p? Of course, it's 0.9.
0.9.
Now, what is the x in this question? What is the x in this question?
Please 1.
I didn't even see your hand raised. You are now, for the first time, in the mood to speak in the class. So you just said it without raising your hand. All right. So x is 1. Now, is x less than 1, greater than 1, equal to 1, or something? Which one? And what makes x what you said? Samuel.
X is exactly equal to 1. I'm
Right.
saying this because if X were to be greater than 1, then we should be told that maybe at least one of them, so we know it's one or more persons living.
Very
And
good.
if it should be less than 1, they should tell us the maximum is 1.
Very good. So then, if X is equal to 1, then the question could have read what? The question in blue could have read what instead of what it reads now? It could have read as what? Instead of how it's reading now, it could have read as what?
Okay,
Please raise your hand. We are not talking into the air. Okay? Whoever is talking, I think that you're making a mistake. Yes, Marilyn.
Yeah, it would be at least one of them.
No.
That should that.
Okay, but that is not how it would have been. Wouldn't have been like that. How would it have been? William.
so it's supposed to be, what is the probability that exactly one of them will leave the company this year?
Exactly. That's how it would have read. Take note of some keywords. What is the probability that exactly one of them? That would have told you that the X is equal to 1. But even though you didn't bring exactly, you should still know by virtue of the sentence. So now that you know this, put yours into the formula, calculate it. So first, identify the elements. Okay, we'll come back to the second part of the question, which is finding the mean and the variance. So these are your elements. Identify the element, then you substitute them into the probability formula like this. You know everything. Okay, so you substitute them. 1 factorial is 1. 3 minus 1 factorial is 2 factorial. Okay. So the top part is going to be 3 times 2 times 1. The second part is going to be 1 times 2. All of that. The 2 cancel the 2 at the top. You're going to have 3. Okay. Then you now multiply that 3 by 0.1 to the power 1, okay, times 0.9 to the power 2. So you have the 3 multiplied by the 0.1 to the power 1, which is this. Then the 0.9 to the power 2 is 0.81, and that will give you 24.3%. Now, what does this 24.3% mean? This is 24.3%, but what does that mean? Looking at this, what does that mean? In relation to this question, what does it mean? Slash.
So please, I think it means that the probability of one person leaving the company is 24%.
Good idea or bad idea? Is that good or bad? Is that a big issue or not a big issue?
It's not a big issue.
It's not a big issue. Yeah, I kind of agree with you. There are some companies I've seen here, okay, in one particular year, okay, the company lost 64% of the employees. Can you imagine? Normally, this thing happens a lot when people don't vote for a particular political party. But in this case, that is what would have been the situation. Now, let's calculate the mean. Okay. Find the mean. And you know the formula for finding the mean. Okay. So, what is the value of the mean? I don't even want to go and show you. What is the value of the mean? If yeah.
This will be 0.3.
How did you get that?
The number of outcomes, that's 3 times the probability, 0.1.
Very good. Excellent, excellent. What is the variance? Or who can show me how to get a variance? What plus what? What times what? What divided by what? What is the variance? I told you to have your pen and paper. I mean, you can't learn this thing without having your pen and paper. Yeah, Frederick.
0.27.
Very good. How did you get that?
the number of trials times the probability multiplied by 1 minus the probability.
Which is what?
0.9. So 0.3 times 0.9.
Times 3. You didn't add a 3. Okay. So that is how it is. That's where you see the variance. Now, looking at the variance and the mean, what can you say? Looking at the variance and the mean. By the way, what is the standard deviation? What is the standard deviation? Somewhere.
I'll calculate it, but that should be the square root of the 0.27.
Masa, I knew what it was supposed to be. That's why I did not give that. If these are the lazy people. Yeah, William.
So the standard deviation will be 0.5196.
Good. 0.52.
1, yeah.
0.52. Guys, I want to ask you a question. Looking at the value of the standard deviation and the mean, what can you say? What you can say is that there's a huge disparity among these values, among the possibilities of someone leaving the company. There are huge disparities among those possibilities. Now, in this case, you selected only 3 employees. Okay? You have N being 3. And the fact that the standard deviation is bigger than the mean shows that there are huge disparities among the employees there. And of course, their probability of leaving the company. Take note of this. This was part of your descriptive statistics, and it's part of the exam question I've set. You should note that. Now, you can also use tree diagram to solve this, okay, without going through the probability formula. But probability formula is very cool. It's very cool than using the tree diagrams. Other than that, yay, you can still use the tree diagram to be able to come out with your work. Now, how do you solve this in Excel? Well, it's a very simple thing. Okay. So what I'm going to do is I'm going to take an Excel data set. Okay. And I think I did have one Excel data set for you guys. I'm going to take the Excel data set, and you want to follow me if you can. I'm going to open an Excel data set. And then I'll use that Excel data set to show you something nice. I think I gave you this Excel data set, didn't I? I did, right?
Yes, please.
Okay. So this was a data set I gave you. Look at it carefully. And I wrote the formula here just so that you can use the formula. Okay. So one of your guys was telling me, how do you calculate this? How do you calculate that and all of that? Well, you calculate that by you knowing the probability. So you can see in this very example that I have given you the sample size, which is 10. Yeah. And I've also given you the probability, which is 20% there. So you can use the binomial formula to find this. This is the entire random variables. Okay? You have the random variable. You can find the probability for each one. This is exactly. And then you can also find the cumulative probability. So if I do for 4, I'm looking at the cumulative probability of all these ones added together to find that. Let's find the probability of 0. The probability that, yes, Selassie.
So in the Excel sheet, your n is 10, but the random variables you have 0 to 10, which is supposed to be 11. Is that supposed to be like that?
Which one?
The binomial, the n, you've written the n, which is the sample size, as 10, and then the one in the yellow, and then the p is 0.2. But the random variables down there, the f of x, is from 0 to 10.
Yeah, we bring the 0 as what do you call it? As a default value. Okay, so you bring the 0 as a default value.
Would you change it to 11 instead of 10?
No. Keep it as 10. If you change it to 11, no problem, but keep it as 10. Okay, because I'm assuming that the 0 is a default value. I'm only trying to show you how you calculate it. If you can change it to 11, but I'm only trying to show you how you calculate it. Or better still, I can keep this at 10 and then move this one out to 9. But I'm just saying that I'm showing you how to calculate the sample size. I'm showing you how to calculate the binomial distribution, other than knowing the exact values that you are going to use. Okay. So if you know these two variables and you are to find the probability of you selecting 0, just bring your equal to symbol and then type binomial. And the moment you start typing binomial, the binomial distribution will show. In this binomial distribution, you now select your sample and then bring a comma and select your trials. And then you can now do a comma and select your probability. But you see, each of the trials is going to be, each of the trials is going to be used. Each of the trials is going to be used in this very Excel. So you can do your FN key down and then press your dollar symbol. Okay. After you selected your trials, let me do that again. So if you select all your trials, you do FN key down and then that. Or you just F4, okay, FN key down, F4. Sorry, wait. Do you see the screen now? Because it went up. FN key down, and then F4, like this. And then you now press your equal to, select your probability, do a comma, and you can now as you can see, you say you should select whether it's cumulative or not. You don't want to do the cumulative, so you say select the false. Okay. And that's it. You press enter. I think, hold on, let me just properly check. So you start binomial. Select your probability. You take the number of trials. And then you select FN F4 key. And then you select your sample size. I just want to be sure that I'm doing the right thing here. And then you do your probability. And then you select whether it is cumulative or not cumulative. I don't know why this thing enters immediately. Okay. I really don't know why it enters immediately. I wouldn't have wanted it to enter immediately, but it's done. It's okay. No problem. Okay. So this is how it's supposed to be. Now, let me show you what I just did and why I decided to do that. If you look at the first one, by the way, when you get the first one, even if these numbers are not there, okay, I'm deleting them. Okay, even if these numbers are not there. So the thing has been imputed already. So now, when you are trying to delete, it doesn't show. But even if the numbers are not there, you just double click at the corner here. Workspace. And then you can now calculate. I think I've put the formulas already in there. So this first one, what it does is that you are calculating, you want to find the exact probability of 0 among these trials, given the sample size of 10. Okay. The only thing you are selecting, okay, is the probability. That's the only thing you are selecting. You are not selecting the 10. The only thing you are selecting is the probability, which is the 2. Okay. And then you select just the 2, no 10. Okay. So if you look here, I've selected A7 to A16, which is a sample size. And then I selected this. Let me see why this is so. What's the next one here? The B phrase. So you don't need this one. Okay. Just enter. Which of you is doing this with me? Okay. All right. Anyway, you select the space, the trials, the sample space here, which is the first one. And then you bring the dollar symbol down. Remember, the dollar symbol is just commanding the formula that every other cell will use those trials, those space, okay, those collectivity. And then you can now pick on the sample size and then the probability and choose false. False because you are not doing the cumulative probability. If you want to do the cumulative probability, you do the same thing. Okay? I'm going to copy the same. You do the same thing here. But this time, we are doing the cumulative probability. Of course, you have to change it. Okay? You are doing the cumulative probability. And so, you select these very number here before you bring the comma. You select this. And then okay, let me do it all afresh. I don't know why my family is being popping. Do you see my screen, by the way? I hope you do see the screen. Do you see the screen?
Yes, we do.
Okay. Okay, so let me start and show that. So you select the binomial distribution function, you select 1, and then you type the 10. You can type the 10 or you can select the 10. Okay. And then you have the probability which you have selected. And then you can indicate that is true. And that true will just calculate the cumulative probability. So that gives you the cumulative probability. You do the same thing for all of the rest here. And now you get the cumulative probability. If you use 2 decimal places, you can see that the last one is almost 1 because the total probability will be equal to 1. So that is how you calculate the binomial probability for a density function and for a cumulative density function. If you change the probabilities, that will change as well. Okay. If you change the probabilities here, that will change. Now, one more thing you can do is that you can also show the distribution of this. So to show the distribution, just highlight everything. Go to insert, select histogram. Select this column. What's the name of this? Clustered column. And then this one here, select that. And then you can now plot this. And this plot will show you the distribution. You can see that it's a little bit, getting to a normal distribution, but it's not a normal distribution. That's why we have the binomial approximation of normal distribution. It's not. Always delete the heading. And then you can label the axis by clicking this chart here. You can use it to, you can click quick layout to just give you the labeling. Okay. And you can then label the axis, delete the title, delete the legend, and then label the axis. Whichever. You can use any of these examples to label the axis. This will help you to see the distribution of these numbers. However, if I change the p-value, if I increase the p-value, anytime you increase the p-value, what you are doing is that you are causing the probability to change. Okay? You are causing the distribution to change in that regard. And so you can change the p-value, which I did increase it here. Okay. So let me show you. I did increase it here, and then you can change it. Yeah, John, your hand is up.
Yeah, sorry, your screen was off for a while, but it's back now.
Okay. If I let me use this one so that we can move faster. Okay. So I decided to run the distribution here for changing the p-value, moving the p-value from 0.2 here to 0.8. And the moment you do that and work out this, if you work out this, you will get this value as that. And of course, you can go here, highlight it, insert, blah, 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 and get this distribution. So this is the first distribution here. Check this. And this is the second distribution here. Check that. And you can see that in the second case, because you've increased the probability, okay, because you've estimated the probability and increased the probability, what happens is that it is more symmetric when the p-value is half. But then as the p-value is increasing, it becomes more negatively skewed. And you can see that in this very example, it is more negatively skewed. This second one is more negatively skewed than that. If I go and change the p-value now, just watch. The p-value, sorry, did I say p-value? The probability value is the same thing. If I change the probability value to 0.5, watch it, 0.5. Check the graph as well. You see the graph changes and becomes purely symmetric. If I change it to 0.1, it becomes more positively skewed. Okay. If I change it to 0.9, it becomes more negatively skewed. So that's exactly the point I'm trying to say. As you change the probabilities, as the probabilities are increased, that is why when the probability is 1, okay, see, when probability is 1, it becomes purely positively, or what you call positive infinity. Okay. So it becomes purely positively skewed. It becomes 1 bar. Of course, that's not what you want. If you want symmetric, you just put the probability into that. Yes, D?
Yes, sir. Please, can you go through the cumulative formula again? It wasn't too clear.
Okay.
I'm struggling here, please.
So for this, the cumulative, all you got to do is type equal to binomial dot distribution. Then you select the X variable, the random variable. In this case, you just select. Once you select, you now come and select, bring a comma, and then pick all of these variables from this cell all the way down to the last one. And then press the FN F4 key to bring the dollar symbol in front of it because you're going to populate the answers. And then you bring a comma and just write true. Okay. So once you bring the comma, okay, watch here. Once you bring the comma, this thing will pop down and you will see whether you have to select true. True is for cumulative distribution function. False means that you don't want the cumulative distribution function. You just want the probability mass function. So once you select true and you enter, it will give you the cumulative. And as you drag them down, as you click here and just drag them down, it will give you for all of them. Is that helpful?
Yes, sir. Thank you. Thank you.
All right. So that is how you do this. Okay? And by the way, guys, I've given you this in the slides. So when you check the slides, you will see all that I did right here. Let me go to the slides. So this is a slide. And in this slide, how to estimate these probabilities are here. The data I used is all there. Okay. How I change the distribution and all of it being negative, you see all of this here. In other words, you should be able to calculate binomial probability once you have the distribution, once you have the probability, and then you have your random variable. So all I need is, suppose I give you a random variable, say 1 to 100. You should be able to tell me the distribution. And then, of course, I'll give you the probability. You need to tell me the distribution of that. That's it. For each one, you tell me both the probability mass function, that is the exact one, and then the cumulative one. So when you are supposed to calculate the cumulative one, you don't need to calculate. You just go and pick these values because they have been accumulated already. Okay, let's go to the Poisson. Poisson is the next one. In the Poisson distribution, it's not the same as the binomial. But the thing about the Poisson distribution is that you are still looking at a random variable. Yes, Samuel.
Sorry to take you back. I wanted to ask, when you were checking the skewness or the distribution using the FX, sorry, you were manipulating the
Samuel.
Of the event happening.
Sorry, we lost you.
Hello, sorry. Okay, so you were.
Samuel, we are lost. We've lost you.
Hello, sir.
You are back.
Yes, please. Sorry, I said that you were manipulating the probability of the event happening to.
Yeah, I was increasing and reducing the probabilities. And that was.
Check the distribution to also look like.
Samuel, sorry, it looks like. Is it only me who cannot hear him?
Yeah, we also cannot hear him. He keeps dropping.
All right. Samuel, see if you can type your question there. That would be great. So that you don't delay anybody. All right.
Say hello.
Yes.
Yes, please. I wanted to ask if
your line is dropped again.
The distribution will also be affected if the n is increased.
Yes. Yes. Okay. If the n is increased, that will affect the distribution. And remember, the n is increased not in the n at the top. Because remember, the n at the top, I wrote it myself. The n is increased with the x's. Because remember, it is from that x we generated the n. So that n is increased looking at the x's, the number. You just look at the number and then you write the n variable. So when you look at the Excel and you look at the x values, you have values like 0, 1, 2, 3, 4, up to 12. So you now know that your n is 13. And then you can now use that n. So you don't just choose an arbitrary n. The n comes from the x. That's all I'm saying. Okay, let's move on. Poisson. The Poisson distribution is often useful when you are focusing on the mean, not just the number, but the mean. Not just a number, but a specified interval of time. You must have a time in mind. You must have a length or space. You must have a space. So anytime you're talking about Poisson, you must have the mean, which is the interval, in mind. It's a discrete value, but the focus is on an infinite sequence of values. Okay? And these are examples. Check each one of them, and you see that the mean is important. You're looking at something happening within a specified time or a specified space. An example, phone calls were received at a reception desk in an hour. So within the hour, how many phone calls were received? So the number of phone calls that are received are restricted to between the hour. That tells you that it's Poisson. Customers arriving at a toll booth per day. You have restricted the thing within the day. The customers are arriving, but they are not just arriving continuously. They are arriving within a specified period of time. That is Poisson. Floors on a length of cable. So the number of floors are within the length. So there's a space, a length of a cable, one length of a cable. That is where the floors are happening. So now you have a specified space. Cars passing using a stretch of a road during the day. During the day is the time gap. So you have a time gap, you have a space gap. That is what gives you a clue that we are dealing with Poisson probability. There are two properties, two characteristics, two features. It's very simple. The probability of occurrence is the same for any two interval of equal length. The probability of occurrence is the same. So if it is 0.2, it's 0.2 all the time. And then the occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence of any other interval. Okay, you see this thing better when we look at the example. Let's take the Poisson formula. Now, the good thing about Poisson is that you are only focusing on the mean, and the mean here is a lambda. E is a natural log. X is the probability of the success that you are looking for. And as for the factorials, we know. So the only thing that you are looking for to find in the Poisson is you want to have the mean. Once you know the mean, once you know the expected value, you can always find the probability of any mass function. And then, of course, you can also find the cumulative probability function. As for the E, it's always 2.71828. It's a natural log. All you need in this is the mean, the lambda. And then, of course, the different X. And of course, based on that, you can find the probability of any number. An example will do the magic. So let's look at an example. Oh, one more thing. In a Poisson, the mean and the variance are the same. The mean and the variance are the same. It's not like the binomial. The Poisson, the mean is the same as the variance. Take this example. Patients arrive at an emergency room of Misericord Hospital at the average rate. You see, now you have the mean. Average rate of 6 per hour. So you have 6 patients arriving every hour. 6 patients arriving every hour on weekend evenings. What is the probability of 4 arrivals in 30 minutes on a weekend evening? What is the probability of 4 arrivals in 30 minutes? Now remember, you were told that the thing is happening within the hour. So if you're now going to have, yes, John, your hand is up.
Yes, yes, sorry. I wanted to ask a quick question. Why is the mean the same as the variance? Does that mean that the values are closely related or almost equal?
Yeah, you got it. It means that, no, it doesn't mean that the values are closely related. Because when the mean is the same as the variance, it doesn't mean that the standard deviation is the same as the mean. Remember, when the standard deviation is even equal to the mean, it means that there is a disparity. There is a disparity. Okay? The only time that the values will be equal is when the standard deviation is 0.
Oh, okay.
That's only when the standard deviation is 0. That's when all the values are 5, 5, 5, 5, 5, 5. Okay? But they are not going to be. They're not going to be. They being equal doesn't mean that the values are of the same numbers.
Okay.
All right. So in this very example, you have to find the mean here. Okay. What is the mean? In this very example, what is the mean? 6 customers per hour. 6 customers per hour. Now, because the question is actually giving us something related to 30 minutes, it means that we are not dealing with the hour. What are we dealing with? Half an hour. Isn't it? Half an hour, 30 minutes. So if you have 6 customers arriving every 1 hour, then how many customers do you think are arriving every 30 minutes? 6 customers are arriving every hour. That is every 60 minutes. So how many customers are arriving every 30 minutes? That's 3. Okay, that's 3. And now the question says that you should find the probability of 4 arriving every 30 minutes. So because that question is asking you, find the probability of 4 arriving every 30 minutes, you have to go and change the 6 per hour to 3 per 30 minutes. Or you can maintain the 6 per hour, okay, but change the 30 minutes to 1 hour, which means that you have to change the 4 to 8. So you are changing 2 things. So it's better to change the 6 to 3 for 30 minutes. That's how you do it. So let's do that here. Okay. So x is 4, lambda is 6. So let's change it to 3 per hour and substitute that value of 3. 3 is the lambda. Okay. You raise the lambda to this, you put it all into the formula, you get 16.8. And that gives you the probability of, and this is from the question, that gives you the probability of 4 people arriving in 30 minutes. 16% chance that 4 people will arrive in 30 minutes is, or 17% chance that 4 people will arrive in 30 minutes. Yes, Frederick.
I wanted to ask, how did you get a 2.71828?
It's a standard thing even on your calculator. So your calculator already has the natural log. Okay, this is a rule which is already in every calculator, every number. The natural log is a number that we know in mathematics, in statistics. It is guaranteed number. Okay, you know, it's like when you're talking about the pi r squared. You know that pi is a number. It's a standard number. Okay? Yes. I've gone through a lot of mathematical rigor to develop it. So this is just a natural log that is already there. It's been there before you were born and before your grandparents were born. And that is something that we know of already. So you just substitute that value. Okay? It's always going to be that value, 2.7182. Please, does that answer your question?
Yes, please. Thank you.
Okay. And then the mean is going to be the variance. We already know that the mean is 3 because it was given in the question. So it means that the variance is also 3. You can plot this. If you have all the numbers, you can plot this probability distribution. And then you see that it is something like that. Okay. How do you do this in Poisson? How do you do this in Excel? It's very simple. Okay. Let's take that the mean is 12 and you want to find the probability that x is 1. Okay. But we need to find some data, first of all. So I'm going to give some particular data here. So I'm just going to go into the Excel. The sheet called Poisson is here. In this sheet, look at it. I have data from 1 all the way to 20. Okay. You have the mean. Yes, Magdalene.
Please, your screen is black.
Oops, sorry. Okay. Please confirm if you can see the screen now.
Yes, please. Yeah. Thank you.
So you have data from here to there, okay, up to 20. This is the only thing that you are giving. And then you are giving the mean to be 12. Okay. These are hypothetical means that you have. You have this mean to be 12. You're going to find the probability that 0 is occurring. Okay. And how do you do that? You just type the Poisson formula. Just type Poisson like this, dot distribution, and then select that random variable, in this case 0, select it. And then select the mean, because all of them are going to use the mean to calculate their probability mass function. You enunciate the dollar symbol in front and behind it. And then, because we are calculating exactly, we are not calculating cumulative, the cumulative is false. And then you just click enter. And once you click enter, you double click the bottom right corner to populate for each of the numbers. And this will give you the distribution for all of them. Now you can see that it's close to normal, as you can see in the graph. By the way, how do you draw this graph? It's very simple. You just highlight all of these like this. Just highlight all of this. Go to insert, choose this one here, insert column or bar chart. Click on that, choose the first one. That's it. Okay. You can now pick on each one of these, see the numbers, each one of these, see the numbers. Touch on each one, and then you can have a feel. You can change even the color if you want to change the color. You know, anything you can just do that. But again, this one tells you clearly that it is normally distributed. Now, watch this. If you actually go and increase the mean, say to 50, okay, you can see once again that it will shift the values. Now, remember, this is the mean. This is the mean, that it should be the right mean. Okay? But I'm just saying that assuming you change the mean to 50, you get that. Okay? And that is because of the nature of the random variables. Okay? If you reduce the mean to 10, okay, you bring it closer to that. Remember, mean is mean. Okay? That is why I put the mean at 12 in this case. And then you can now see what the distribution will look like in this case. Let me just remove this. But how do you get a cumulative distribution? The same way, the same Poisson dot distribution, and then this time choose true. Then you can now get a cumulative distribution. Getting to the end, you can see that the cumulative distribution, getting to the end, everything will be towards 1. So in the last one here, you can see that it's 0.99, which is approximately 1. That's how you find the cumulative distribution. So using these two information, you can always find that of the values. This value was already in the Excel. Okay? The probability that X is 1 was in the Excel. You can also find the probability that X is less than 4. It's simply finding the cumulative probability. Okay? And which, if you go and check, you see that that cumulative probability is this value. And then, of course, the distribution is what I've already shown you here. So that is how you exercise your right in understanding Poisson and binomial distribution. Here is my takeaway. Number 1, note that the binomial distribution and the Poisson distribution, there's a difference. Whereas the binomial distribution gives you the exact probability, the Poisson gives you the mean probability. That's what you should take note of. And then based on the exact probability or the mean probability any of them has given you, you can find the probability mass function, which is exact, or the probability, cumulative probability density function, which is the cumulative. Whether it is more than, less than, equal to, you can find any of them once you know that. I get to know the difference. Poisson will always tell you something within a certain interval, either time interval or space interval. Also know the mean and the standard deviation for a discrete random variable. A random variable whose probability you don't know, okay? All of these two, we know their probabilities now. But remember in the earlier one, we looked at a random variable whose probability don't know. Please, if you don't understand anything, two things you can do. You can contact me and I'll walk you through it myself. You can ask your question in the group page, or you can watch the video again. And if you still don't get it, let me know. Have some specific questions if you don't know. Okay. And look at the book. Look at the book by Anderson et al., the book by Evans et al. And then you will have a lot of these examples for you to work on with solutions to working on some. All right, ladies and gentlemen, that brings us to the end of the entire caboodle.